Distributed database systems. Parallel query evaluation in distributed database systems. Objective: speed up query execution by processing parts of the query simultaneously across multiple nodes in the distributed system. Key techniques. Interquery parallelism: execute different parts of a single query in parallel. Interoperation parallelism: parallelize within a single operation, e.g., parallel scan or join. Interoperation parallelism: execute multiple operations of a query plan concurrently, respecting dependencies. Strategies. Partitioning: data and task divide the data and computation among available nodes. Pipelining: output of one operation is directly streamed to the next. Load balancing: distribute work evenly to avoid bottlenecks. Example: a select query over a large table partitioned across 3 nodes can have each node scan its local partition simultaneously and return partial results for merging. Distributed transaction processing. Objective: ensure correctness, atomicity, consistency, isolation, and durability, ACID properties, for transactions executed across multiple nodes. Core components. Two-phase commit protocol, 2PC. Phase 1, prepare coordinator asks all participants to prepare and vote. Phase 2, commit/abort if all vote yes, commit, else, abort. Concurrency control. Distributed locking, e.g., 2PL. Timestamp ordering. Failure handling. Use of logs, undo/redo operations, and recovery managers. Challenges. Network latency and failure. Ensuring consistency in presence of partial failures. Deadlock detection and resolution. Future trends in distributed databases. Cloud-native databases. Databases designed for scalability, elasticity, and multi-tenancy in cloud environments. Integration with AI and big data. Distributed databases are becoming the backend for AI model training, inference, and analytics. Blockchain-based distributed databases. Decentralized data storage with immutable ledgers. Multi-model databases. Support for relational, graph, document, and key-value data models in a unified system. Conclusion. Distributed database systems have evolved to support the modern digital ecosystem, enabling fast, reliable, and scalable access to data across geographically dispersed nodes. While their design and implementation present several technical challenges, including transaction management, query optimization, and fault tolerance, the benefits of increased reliability, performance, and flexibility are unmatched in large-scale applications. Understanding the fundamental principles of data fragmentation, replication, parallel processing, and distributed transaction management is crucial for designing efficient and resilient distributed database systems in today's interconnected world. Object-oriented and object-relational databases, concepts and applications. 1. Introduction. With the evolution of data-intensive applications, such as multimedia systems, engineering design, geographic information systems, GIS, and artificial intelligence, traditional relational databases often fall short. To meet the need for more complex data modeling, semantic richness, and behavioral encapsulation, 2 major database paradigms have emerged. Object-oriented database systems, OODBMS. Object-relational database systems, ORDBMS. These systems combine the strengths of object-oriented programming, OOP, with the robustness of database technologies, aiming to bridge the gap between application data models and database schemas. Object-oriented databases, OODBMS. 2.1 What is an OODBMS? An object-oriented database management system integrates object-oriented programming principles, encapsulation, inheritance, polymorphism, directly into database systems, allowing objects to be persisted, queried, and shared. Instead of breaking objects down into tables and rows, as in relational databases, OODBMS stores objects as they are, preserving their internal structure and behavior. 2.2 Core features. Encapsulation, data and associated behavior, methods, are stored together. Inheritance enables new classes to reuse properties of existing ones. Object identity, OID. Each object has a unique identifier, independent of its values. Complex objects can be nested or aggregate other objects. Persistence, objects outlive the application execution and can be stored and retrieved later. Versioning, support for managing different object versions, useful in design and engineering apps. 2.3 Object Data Model. The data model includes classes, define object structure. Attributes, data members of the class. Methods, functions that operate on data. Relationships, associations like aggregation, composition. 2. For OODBMS query languages. Examples include OQL, Object Query Language modeled after SQL but supports object navigation. LINQ, in .NET allows querying of collections and databases using objects. 2.5 Advantages of OODBMS. Closer semantic alignment with application code. Better support for complex data, images, video, CAD models. Reduced impedance mismatch between application and database. 2.6 Disadvantages. Less mature than relational systems. Poor support for ad hoc querying, compared to SQL. Limited interoperability with standard tools. 3. Object-Relational Databases, ORDBMS. 3.1 What is an ORDBMS? An object-relational database management system combines features of relational databases with object-oriented concepts. It maintains the relational table structure but adds support for user-defined types, UDTs, table inheritance, methods and encapsulation. 3.2 Enhancements over RDBMS. Custom data types, define complex types, e.g., address, point, polygon. Inheritance. Tables can inherit properties from other tables. Polymorphic queries. Row types and nested tables. Temporal and Spatial Databases, managing time and space in data. 1. Introduction. In the modern data landscape, not all information is static. Many applications require tracking how data changes over time, temporal aspect, or where the data applies, spatial aspect. Traditional relational databases lack built-in support for these dimensions. To address this, temporal databases and spatial databases were developed, each enhancing database systems with capabilities to model, store, and query time and location-based information. Temporal and spatial databases are critical in geographic information systems, GIS, financial systems, medical records, transportation, IoT, and environmental monitoring, among others. 2. Temporal databases. 2.1 What is a temporal database? A temporal database is a database that supports the storage of data with time-related attributes. It allows users to track historical, current, and future states of data. 2.2 Types of time in databases. Valid time, VT. When the fact is true in the real world. Transaction time, TT. When the fact is stored in the database. Bitemporal data, combines both valid time and transaction time for full temporal tracking. 2.3 Temporal Data Model. Temporal extensions to the relational model include timestamped tuples or columns, e.g., valid_start, valid_end. Temporal integrity constraints, e.g., no overlapping intervals. Temporal primary keys, uniqueness over time. 2.5 Applications of temporal databases. Medical records, patient treatment history. Banking systems, account balances over time. Version control, document revisions. Inventory tracking, stock movement history. 2.6 Advantages. Precise historical analysis and auditability. Handles retroactive and post-active updates. Enables data rollback and time travel queries. 2.7 Challenges. Schema and storage complexity. Temporal joins and indexing performance. Lack of support in many commercial RDBMS. 3. Spatial databases. 3.1 What is a spatial database? A spatial database stores and manages geometric data such as points, lines, polygons, and 3D shapes. It enables queries like distance, overlap, containment, and nearest neighbor. 3.2 Spatial data types. Common types. Point, a single location, e.g., a sensor. Line string, a path, e.g., road segment. Polygon, a region, e.g., city boundary. Multipoint, multi-polygon, collections of shapes. 3.3 Spatial indexing. To efficiently retrieve spatial data, indexing methods are essential. R-tree, hierarchical, bounding box-based indexing. Quad-tree, recursive spatial partitioning. Grid indexes, regularly spaced grids. 3.4 Spatial query operations. Range queries, find all points within a region. Nearest neighbor, closest location to a point. Intersection/containment, identify spatial relationships. Spatial joins, combine spatial and non-spatial data. Conclusion. Temporal and spatial databases have become fundamental for modeling the dynamic nature of the world, where time and location are intrinsic to the data. Big data storage and processing, Hadoop, HDFS, and beyond. Overview. With the explosion of digital data from social media, IoT devices, sensors, logs, and transactions, traditional databases struggle to handle the volume, velocity, and variety of data, known as the three versus of big data. To address this, big data storage and processing systems have emerged, offering distributed frameworks that scale horizontally and process data efficiently in parallel. What is big data? Big data refers to massive datasets that are too large or complex for traditional data processing software to manage. These datasets can range from terabytes to petabytes and contain structured, semi-structured, and unstructured data. Key technologies for big data storage and processing. 1. Hadoop ecosystem. Hadoop is an open-source framework designed for distributed storage and parallel processing of large datasets. Developed by the Apache Software Foundation, Hadoop's architecture is fault-tolerant, scalable, and designed to run on commodity hardware. 2. HDFS, Hadoop Distributed File System. HDFS is the storage layer of Hadoop. It breaks down large files into blocks, default 128 megabytes, and stores them across multiple nodes. Each block is replicated, default 3 times, for fault tolerance. Consists of name node, master maintains metadata and namespace. Data nodes, slaves store actual data blocks. 3. MapReduce. The original processing model in Hadoop. Performs distributed data processing in 2 stages. Map, processes input and converts it into key-value pairs. Reduce, aggregates the output of the map phase. 4. YARN, yet another resource negotiator. The resource management layer in Hadoop. Enables multiple applications, MapReduce, Spark, etc., to share resources. Use cases of big data storage and processing. Healthcare, predictive diagnostics using large patient data sets. Retail. Customer behavior analysis for recommendation engines. Finance, fraud detection through transaction pattern analysis. Smart cities, sensor data processing for traffic and pollution control. Social media analytics, sentiment analysis and trend forecasting. Beyond Hadoop, next-generation big data technologies. 1. Apache Spark. A faster alternative to MapReduce within memory processing. Supports batch and stream processing, machine learning, mlib, and graph processing, GraphX. Compatible with HDFS and other storage systems. 2. Apache Hive. SQL-like querying interface on top of Hadoop. Converts SQL queries into MapReduce jobs. Challenges in big data systems. Data quality and cleaning. Security and privacy. Real-time processing needs. Storage optimization. Scalability and fault tolerance. Chart increasing conclusion. Big data storage and processing technologies like Hadoop, HDFS, and Spark have transformed how organizations manage vast and fast-growing datasets. These systems allow scalable, fault-tolerant, and efficient data analytics, fueling insights across domains from healthcare to finance. Cloud databases, architecture, services, and security. 1. Introduction to cloud databases. Cloud databases are databases that run on cloud computing platforms and provide access to data through cloud-based infrastructure. Unlike traditional databases hosted on-premises, cloud databases are scalable, managed remotely, and accessible over the Internet. 2. Architecture of cloud databases. Cloud database architecture generally includes multi-tenant architecture. Multiple customers share the same infrastructure but have isolated databases. Elastic scaling, automatically scale up or down based on demand. Distributed storage, data is replicated across multiple servers and regions for fault tolerance. Decoupled storage and compute, improves efficiency by separating data storage and processing units. Deployment models. Public cloud, hosted by third-party providers like AWS, Azure, GCP. Private cloud, hosted on private servers for a single organization. Hybrid cloud. Combination of both public and private models. 3. Cloud database services. Cloud providers offer different service models. A. Database as a service, DBaaS. Fully managed databases, e.g., Amazon RDS, Google Cloud SQL. Provider handles updates, backups, and scaling. B. Infrastructure as a service, IaaS. Users deploy and manage databases on cloud virtual machines, e.g., MySQL on EC2. C. Platform as a service, PaaS. Integrated platform to develop and manage applications with embedded database services, e.g., Azure SQL Database. 4. Types of cloud databases. Relational cloud databases, support SQL, ACID properties, e.g., Oracle Cloud Database, Amazon Aurora. NoSQL cloud databases, optimized for unstructured and semi-structured data, e.g., MongoDB Atlas, Amazon DynamoDB. NewSQL cloud databases, combine scalability of NoSQL with relational model, e.g., Google Spanner. 5. Advantages of cloud databases. Scalability, instantly scale resources up/down. High availability. Built-in redundancy and failover. Reduced maintenance, providers manage updates, security, and patches. Global accessibility, access from anywhere via the Internet. Cost-effectiveness, pay-as-you-go pricing reduces capital expenses. 6. Security in cloud databases. Ensuring security is critical due to remote access and shared resources. A. Data encryption. At rest, encryption using AES 256. In transit, TLS/SSL encryption for data transfer. B. Identity and access management, IAM. Role-based access control, RBAC, and multi-factor authentication, MFA. C. Compliance and auditing. Cloud providers ensure compliance with regulations, GDPR, HIPAA, ISO/IEC 27001. Logging and auditing for access and activity tracking. D. Backup and recovery. Automated and scheduled backups. Point-in-time recovery and failover solutions. Conclusion. Cloud databases are transforming the data management landscape by offering scalable, flexible, and secure solutions across industries. NoSQL databases, scalability and flexibility beyond relational models. Overview. As data volumes grow exponentially and applications demand high availability, scalability, and flexibility, NoSQL databases have emerged as a powerful alternative to traditional relational database management systems, RDBMS. Designed to handle large-scale, distributed, and diverse data, NoSQL databases support modern use cases such as real-time analytics, IoT, content management, and cloud-native applications. What is a NoSQL database? NoSQL stands for Not Only SQL, a category of databases that diverge from the rigid tabular structure of SQL-based systems. NoSQL databases are schemaless, non-relational, and optimized for horizontal scaling and fast data access. They are particularly useful when The structure of the data is variable or semi-structured. The application requires high-speed read/write operations. The system must scale to millions of users or devices. Traditional RDBMS can't meet availability or partitioning needs. Types of NoSQL databases. Document-oriented databases. Store data as JSON, BSON, or XML documents. Ideal for hierarchical data and complex nested structures. Examples: MongoDB, CouchDB, RavenDB. Key-value stores. Store data as key-value pairs for ultra-fast lookup. Often used for session management, caching, and user profiles. Examples: Redis, Ryak, Amazon DynamoDB. Column family stores. Organize data in column families rather than rows. Great for analytical workloads and wide data sets. Examples: Apache Cassandra, HBase, ScyllaDB. Graph databases. Model data as nodes and edges to represent relationships. Ideal for social networks, recommendation engines, fraud detection. Examples: Neo4j, Amazon Neptune, ArangoDB. Small blue diamond key features and advantages. Schema flexibility, no rigid table structure, data model can evolve with the application. Horizontal scalability, easily distribute data across many servers or data centers. High performance, optimized for fast access and real-time processing. Fault tolerance, many NoSQL systems support replication and eventual consistency. Big data ready, suitable for petabyte-scale datasets. Use cases of NoSQL databases. Social media, storing user-generated content and relationships, e.g., likes, comments. IoT systems, handling sensor data that arrives in unpredictable formats. E-commerce, product catalogs, user sessions, and shopping cart data. Gaming, real-time multiplayer states, leaderboards, and user data. Content management systems, managing documents, blogs, and multimedia files. Challenges. Lack of standardization, different APIs and query languages per system. Data integrity, limited support for transactions and constraints. Learning curve, developers and DBAs must adapt to new paradigms. Eventual consistency, may not suit applications that require strict ACID compliance. Conclusion. NoSQL databases offer a powerful alternative to traditional databases for modern, data-intensive applications. Multimedia databases, managing images, audio, and video content. Multimedia databases are specialized systems designed to store, manage, retrieve, and manipulate media types such as images, audio, video, animations, and graphics. Unlike traditional databases that handle structured data, e.g., numbers, strings, multimedia databases deal with unstructured or semi-structured data that often require complex indexing and retrieval mechanisms. 1. Characteristics of multimedia data. High volume, multimedia data files are large in size, requiring significant storage and optimized retrieval strategies. Variety includes different formats like JPEG, MP4, MP3, WAV, AVI, etc. Complexity, metadata, e.g., duration, resolution, must be stored and linked with actual content. Temporal and spatial properties, videos and audio have time-based attributes, while images and graphics have spatial properties. 2. Multimedia data types. Image data, photos, satellite images, medical scans, e.g., X-rays, MRIs. Audio data, speech, music, and environmental sounds. Video data, surveillance footage, movies, interactive media. Animation and graphics, 2D/3D models, CAD files, game assets. 3. Storage and compression. Storage strategies, use of dedicated file systems, blob storage in relational or NoSQL databases. Compression techniques, JPEG, MPEG, MP3 are used to reduce data size without significant quality loss. 4. Indexing and retrieval. Content-based retrieval, CBR searches are based on image color, shape, or audio pattern instead of keywords. Text-based indexing, metadata tagging or captions used for querying. Hybrid models, combine content-based and metadata-based approaches. 5. Querying multimedia data. Similarity queries, find images similar to this, or retrieve audio with similar rhythm. Spatiotemporal queries, locate video scenes with specific motion patterns or timestamps. Multimodal queries, cross-type searches like finding a video using a related image. 6. Applications. Digital libraries and archives. Social media platforms. Surveillance and security systems. Healthcare imaging systems. Entertainment, streaming services, music platforms. 7. Challenges. Standardization, diverse formats and encoding make integration complex. Performance, high latency due to file size and processing. Security and copyright, managing ownership and secure access. Semantic gap, bridging the user's query intent and the actual content. 8. Multimedia Database Management Systems, MMDBMS. Examples: Oracle Multimedia, Microsoft SQL Server FileStream, IBM DB2 with multimedia extensions. Key features include media storage and format support, content-based indexing, advanced query capabilities,